Today, we're diving into a technology that's quietly wrapping our entire planet in a digital skin, creating something that's kind of like a global nervous system. I mean, just think about that for a second. What if our world could feel temperature changes, see movement, and then communicate what's happening from anywhere, instantly? Well, that's not science fiction anymore. Welcome to the world of wireless sensor networks.
So what exactly is a WSN? Well, at its core, it's a huge team of tiny digital reporters. They're scattered all over the place, each one sensing a tiny piece of the world, and then basically gossiping with its neighbors to pass that message along. So, what can you do with a planet-sized nervous system? Let's start with something that feels like it's straight out of a movie.
Yeah, one of the wildest applications for these things is tracking a moving target. Could be a person, a vehicle, even an animal. But how do you actually do that without burning through a ton of energy? Turns out there are a few really clever ways. First up is what we call the push-based method. As soon as a sensor spots the target, it immediately shouts out its position to the whole network. It's like a live, non-stop stream of updates. Super thorough for sure, but it's also really noisy and, you guessed it, a major battery drain. The second way to do it is pole-based. Now in this case, the sensors see the target, but they keep quiet. They only report back when the central system pulls them, basically asking, hey, you see anything over there? This is way more energy efficient. It's kind of like only checking your phone for messages when you want to, instead of getting pinged with notifications all day. And the third method, called guided, is where it gets really smart. Instead of every sensor reporting, just a few key nodes work together to create a virtual path that leads right to the target. It's like leaving a trail of digital breadcrumbs for a tracker to follow, guiding them straight to where they need to go. And the thing is, this whole process isn't just random. It's this elegant six-step dance. It all starts with the nodes cooperating. Then they compute the target's position. They even try to predict its next move, all while carefully managing their power. And if they lose the target, there's even a recovery step before the final detection. It's just a remarkably complex and beautiful system.
But these networks aren't just for playing a high-tech hide-and-seek. They're giving us senses in places we've never had them before, from our farms to the most remote corners of the wilderness. Take agriculture, for instance. A really simple system can protect a whole field. First, a passive infrared sensor, a PIR sensor, detects body heat from, say, an animal trying to get in. As soon as it senses something, it wakes up a second ultrasonic sensor, which then measures the object's exact distance. Simple, cheap, and unbelievably effective.
Now, these networks basically have two types of senses they can use. On one side, you've got your scalar sensors. These are the cheap, low-energy workhorses that send simple things like temperature or light from all directions. And on the other side, you have camera sensors. They capture amazing, rich video and audio, but they're expensive, they're total power hogs, and you have to point them in just the right direction. So you know what's next, right? Why not get the best of both worlds? And that's exactly the idea behind wireless multimedia sensor networks. You can scatter a ton of those cheap scalar sensors to detect that something is happening, and they can then wake up the one expensive camera sensor you need to see exactly what is happening. This combination just opens up so many incredible possibilities. I mean, for security surveillance, monitoring wildlife habitats, or tracking environmental changes, sometimes simple data just isn't enough. You really need to see what's going on. This combo gives you precision and detail without having to spend a fortune. But what happens when you take these networks into an even crazier environment?
So, on land, sensors use radio waves to talk, but those waves don't travel very well underwater. So down there, networks have to communicate using sound, acoustic signals. But the deep ocean, it has its own challenges and its own villains.
Meet the soliton. It's this massive, weird internal wave that moves under the surface of the water. And it turns out, these waves are one of the biggest disruptors of underwater communication.
See, these solitons act like this chaotic noise that just scrambles the acoustic signals passing between sensors. When a sound wave hits one of them, it scatters, making communication totally unreliable and just torpedoing the network's performance. It's like trying to have a conversation in a room where the walls are constantly shifting.
So whether you're on land or deep in the sea, when you're deploying thousands of these tiny sensors, you run into a really fundamental design problem. How do you possibly make sure your network can see everything it's supposed to see? And maybe just as important, how do you make sure all those sensors can talk to each other to report back what they find? So you have these two key goals, coverage and connectivity. Coverage is all about getting rid of blind spots,
And connectivity is making sure that the data from any one sensor can actually find its way back home. Now, you'd think these are two totally separate, really complex problems to solve. But they're linked by one beautiful, simple rule. And here it is. This is the golden rule. As long as each sensor can talk at least twice as far as it can see, then if you solve the coverage problem, you automatically solve the connectivity problem for free. It's an incredibly elegant principle that lets engineers design these massive, reliable networks.
So we've gone from fields to forests to the bottom of the ocean. What's next for this global nervous system? Well, the next step is to shrink it all down to a scale that's almost impossible to imagine.
Welcome to the world of nanonetworks. We're talking about sensors so small they could communicate inside the human body or build microscopic machines. And there are two main ideas being explored. One uses electromagnetic waves, way up in the terahertz band, broadcast by tiny graphene antennas. The other one, molecular communication, is even wilder. It literally uses molecules to carry information, packing data into these tiny biological packages called vesicles.
So, from monitoring our fields to someday communicating inside our very own cells, wireless sensor networks are giving our world, and maybe even our bodies, a nervous system. It's a technology that's becoming more powerful and more invisible every single day. Which really just leaves us with one final thought. As we build this sentient planet, what are the right questions to ask it?